Now, this is a short talk. We've only got 30 minutes, and you'll all be keen to get your lunch. And we've got a lot of content, so I'm going to rattle through this. The whole team's here, and we're going to all talk about different aspects of what we're doing. I'm going to start by giving you guys the elevator pitch. We'll talk about more things in more detail, and it's going to climax with a live demo by Lucas. So what could possibly go wrong? So Cmajor. Cmajor is our new language and runtime and platform for audio development. We've been working on it for about a year. We have the main goals we've got in the project is to do a better job than the current status quo of C++ and native development. We're aiming to be able to write code once and run the same code on diverse platforms. And by diverse, I don't mean ARM and Intel. I mean actually, diverse CPUs, DSPs, TPU, whatever weird architectures are around. We're going to get optimal performance out of every platform, and performance is a big deal for us. We'll talk about that in more detail in a minute. We want this thing to be really easy to learn, so easier than C++, which is not difficult, but really beginner-friendly. We're aiming to also speed up the actual professional development pipelines and actually be able to deploy faster and get faster product development cycles out of this. And we want it to be crash-free and sandboxed and safe because I don't want people to be writing plugins that I install it on my machine and it comes and gets my bank details and installs a Bitcoin miner. So I'm going to talk first about the sort of platforms we're targeting with this. As an audio developer, it's even keeping a product running on Intel and ARM is a huge hassle. Big companies have whole DevOps teams dealing with this, and what ends up happening is even on CPUs, a lot of code doesn't end up taking advantage of even the latest SIMD instructions that are available because actually writing some generic C++ that can take with different code paths for different architectures and extensions is a total pain, and generally ends up not being worth the effort. And also now we've got lots of developers coming along and wanting to do algorithms. Machine learning is getting really big. Lots and lots of people are trying to get that stuff going. And it'd be really great if your machine learning algorithm could take advantage of I'm sure this laptop here has probably got some AI accelerator stuff inside it. It'd be really nice if the code you wrote could just magically take advantage of that. Some people are even writing sort of extremely parallel stuff that could take advantage of even a GPU. And it'd be really nice if the code we wrote naively could just run on a GPU if you happen to be, in that small category of really parallel problems. So what we're trying to do with Cmajor is build something where the code you write has a structure that's future-proof, and where parallelism in the code is expressed in a really natural way as a graph, which works really nicely for most audio coding. We're going to combine that with a JIT engine so that we can take advantage of running that on each target platform, taking full advantage of everything that platform can do, without you actually ever needing to know about that or update your code or make any changes when new processes come out. In terms of productivity, we all love C++. I write it every day, but the whole compile, test, release cycle is slow. We can do better than that. The web people just write JavaScript and hot reload it, and we can do that too, without losing any performance. Also, when you get to the more professional end, you find that in a lot of bigger companies, you'll have DSP developers. The DSP, sort of more mathematicians developing DSP, which they'll prototype in something and then pass it on to be completely rewritten by another team in C++. And what we kind of want to do is be able to have a tool that blurs the lines between the prototyping and the experimentation and the actual production code to make that whole system a bit more efficient. We also want to allow sound designers to get a bit more control over what's going on, in that loads of sound designers, they might be making a sound that needs a little tweak here and there, but to get that little bit of extra DSP into a particular sound, they have to put a request into the development team and wait for days and days for that to be approved and someone to write it and add it to the underlying instrument. And it's slow, and it's, again, it's stuff that we can improve on. We also want this thing to be easy for beginners to use. I mean, it's a low bar to be better than C++, but we're also going all in with really boring technologies for our glue code and GUI. So we get JSON, HTML, React interfaces, and lots of JavaScript, stuff that everybody knows for the non-time critical parts of what you're building. We've got a really nice thing which we'll show you, you'll see it running in a moment, which is that if you want to use Cmajor and VS Code, it's literally you go to, and you can do this today because we've just launched it, I think it's live. You just go to the VS Code, type Cmajor in the extensions panel, click install, and you're done. There's no path to set, no tools to install. You can then go to a piece of Cmajor and hit F5, and it will play it at full speed. And that's as simple as that. So really, really easy. And that's the tool that we're going to continue expanding on, turn into a really great little integrated development environment. And then that's what we've got at the moment. Coming next, we'll have all the fancy browser-based playground side of things, because we can run our code quite happily in the web. And eventually, because we've got a graph-based structure, we can get onto visual editing tools for that. So next, I'm going to get out of the way and pass it over to Cez, who is going to talk about the performance, which is very close to our hearts with this.
Right, hopefully that's working. Yeah, as Jules mentioned, we've got a JIT compiler, and I wanted to talk about a few things about JITting code and why everyone should be doing it, and unfortunately why they're not at the moment. So if you think about a typical plugin build at the moment, you're probably targeting x64 and ARM. But when you say x64, you're probably talking about an architecture that was specified in the late 90s. So if you think about what an x64 target is, it predates a large number of extensions, SSE extensions that have been added, things like AVX. So when you just say, build an x64 executable as a plugin, you are throwing away about 20 years of progress in CPU design. Okay, the modern processors will run those instructions faster, but it would still work on a much older machine. JIT technology as a basic starting point is the equivalent of doing a native build of some C++, where you target the actual machine you're sat at. Now you could go out of your way and use those sorts of techniques with binaries, but you end up back in this whole development, build, test, multiple versions of libraries, choosing the right one at runtime, blah, blah, blah. It's a pain. So we get significant benefits from targeting the actual hardware the user is running on. We've also got vector support in the language, which is another thing that, again, when you're writing C++, you have this issue that the Clang compiler or whatever compiler you're using has to infer the parallelism in the data structures you're using and generates SIMD instructions from that, unless you go out of your way and write a load of SIMD intrinsics, and then you're back in this, which machine am I targeting? Is it Neon? Is it AVX? La, 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 and you're back in that horrible, unpleasant world. So again, we get advantages from there. We also have designed the language to not have aliasing problems, which again is a big issue for C++, where performance gets left behind because parallelism would imply reading and writing memory in ways that may not be safe. And again, the Clang has to be quite conservative about decisions it makes. We don't have those issues. And the other thing that we do is have no sort of exception cases which would cause, again, memory to be left in a weird state if you were to parallelize an algorithm, but then an exception be thrown. So again, C++ suffers from, like by default, from issues where it can't necessarily parallelize algorithms, even if it knows that it looks like it's parallelizable. So what does this mean in practice? Well, I've been looking at an algorithm that is a sort of typical machine learning type runtime. So it's a matrix type algorithm. And I've compared an implementation using Eigen, which is, if people don't know, a high-performance matrix library for C++, compared to the same code rewritten in Cmajor. I've got a set of architectures here, and we see that our Cmajor implementation outperforms Eigen quite considerably. The main obvious one is an x64 AVX machine, where we are nearly 4 times faster. The reason for this is we're talking about AVX. We're getting AVX benefits when the Eigen implementation by default is assuming we don't have those extensions. If you did a recompilation saying and include AVX, it will double in performance, which actually isn't all the way there, but it's quite a lot of the way there. And we see across the board, a very important takeaway is don't run high-performance code on a Raspberry Pi. And the modern M1 Max Apple machines are awesome. That's the other important takeaway from that. So I'm going to hand it across to Harriet.
Thank you. Thanks, Chez. All right, let's talk using it. So batteries included. Hey, we've got a standard library. Woo, yeah, it's great. I've been writing documentation for it. Go and use it, it's great. If you see a bug, message me, don't tell Jules, I'll get in trouble. Anyway, so what does this mean? We've obviously targeted audio things, so we've got tons of filters that are really useful, I think. We've got Butterworth, TPT, DC blocker, things like that. They use as processor objects, so they can be placed into graphs, and we'll go into more detail about structure of Cmajor a little bit later. We've got some fixed and dynamic ADSR envelopes, common oscillators, sine, LFO, wave shapes, things like that. And we can handle raw MIDI data, which is great. We've got timeline. Have I written timeline there? Yeah, we've got timeline, so that can take information from the host or from the DAW, style things like that. So this is our standard library as is now. There's a few other bits that I haven't put on the slide here, but it's constantly being updated. Our online docs are auto-generating to show this, and I'd say if you want to start using Cmajor today, look at the standard library and look at our examples, and you'll see very quickly how things work and how to get your way around it. So without further ado, let's do a live demo. I'm going to pass over to Lucas now.
Yeah, we've done pretty well to get to rattle through the boring bit. Now Lucas is going to attempt without a safety net. This is what we wanted you to see.
So, that's good. All right, so as well as providing an embeddable runtime for compiling and running C++ in your existing applications in whatever way you like, we also introduced the concept of a patch. And a patch is really just a bunch of files pulled together in a JSON manifest like we've got here. And it's intended to be consumed by audio host applications. So there's some metadata that a DAW might use to populate its menu, and then you list some source files. We've only got one here, but this could be an array, and this is how you'd share some DSP code across your patches. But as Jules mentioned, we're in VS Code. I'm looking at a patch manifest. So if I press F5, it should run in our patch player. And we've got raw audio and MIDI routed through the top level graph. So if I had a MIDI controller, right, lovely. So whilst this is open, I want to demonstrate a few things that these tools enable in terms of your workflow. So if we go into the DSP code, I mean, it doesn't really matter what any of this does, but the point is that I can change it. So if I go down here where we've got routing stuff to the outputs, I can route one of the standard library oscillators, for example, into a gain. If I save it, this is now attenuating the gain. I can get rid of it, and it live recompiles and swaps in. And another thing we can do is essentially reload the GUI. So this is our default GUI that you get just by declaring parameters and stuff at the top. And you see there's different controls. So we've got switches and drop downs and stuff. And the point is that these come up a combination of type information here and these things here called annotations. So if I get rid of the annotation, for example, that switch goes away. And if I get rid of Boolean, for example, it's a knob and not a switch. And this UI, as Jules mentioned, is built using web tech. And it communicates with the runtime by sending JSON structures back and forth over a communication channel. And you can, instead of having this default UI, write your own custom one in whatever way you like. So this example I've got here is a monosynth inspired by a web app called Subtract 1. So if we look at that quickly, Subtract 1, an analog-inspired subtracted monophonic synth powered by 3 oscillators, a filter, and 2 envelope generators. It's completely written in JavaScript using the Web Audio API. So this is a web app, and the author, Julius Storer, has made the source available on GitHub. So we can write a UI like this in the exact same way, but instead of using the Web Audio API to plug together nodes from their API, we can plug together stuff from the standard library that Harriet mentioned, so filters and oscillators and stuff. So if we go back to the manifest, another thing you can define is a view property. So if I put this here, this is the default UI. If I save that, now you get this UI. So as we saw earlier, this is mostly input and output. Well, there's mostly input parameters, but we've got a couple of output parameters declared in the top level graph. So this particular UI uses MIDI note information to keep this scope, oh, what am I looking at? Scope always locked at a consistent zoom level. And I have to send snapshots of the audio data to get that UI at all. And this particular web UI is built using React in Redux, which made porting it into Apache UI really quite straightforward. Redux, which is this state management library, has this concept of a single source of truth called a store that you can hook into. So all UI updates go through that, and you can hook in there. I just route that via our patch connection. And then if the C++ backend actually does anything, I get told about that and actually let it update the UI. So this was very quick to port. But we did change one important thing, which is all of these controls we changed so that they send events at the start and end of each gesture, which is important for recording automation in a DAW. So speaking of DAWs, another thing you can do with our tooling is generate a JUCE plugin. So this spits out some C++, which I already did earlier. It uses our C++ backend of the compiler to compile the Cmajor to C++. And then it gets all pulled together in a CPP that glues that into a JUCE plugin and embeds all these web resources, so it's self-contained. So if we go to a DAW, we also ship a JIT plugin. So all those live reloading workflows, you can use this plugin for. But here's the ahead of time compiled plugin in a DAW. So does the same thing. You change the automation parameters, it changes the GUI, and now you're in a DAW, you can use all your other good stuff, like an arpeggiator or whatever. So that's roughly the demo. We also have a WebAssembly backend for the compiler, so you can put this thing back in a web browser. And I hope that gives a sense for how productive it can be to build tools with this. And as a result of writing things in this way, you end up with a nice decoupled bit of DSP and GUI code. So let's get the slides back up, however I do that. Stop mirroring. How do you use a computer, Jules?
You're asking the wrong person.
Honestly,
We got it? Yeah. Cool. Yeah, and that's brilliant because that completes our unbroken run of me and Ches never having a crash during a live demo so far. Yes. It's going to come to an end pretty soon. So we're doing really well for time. I want to leave some time for questions, but the sort of TLDR for all this is like, this is what we're building. It's like really nice, easy to learn, C-like language with a really cool name that optimizes really, really well. We have graphs in there so that we can model your parallelism. We're going to use really boring, webby GUI and glue code. We've got a great JIT engine. We've got a C++ API, which lets you take our JIT engine and embed it in your own app if you want to do that. So we've got examples of little C++ apps where you can open our JIT engine, give it some Cmajor code, crank the handle, it'll render it. So you could use that in a DAW or something. We've got the code generator, which does C++ and also spits out WebAssembly. And we've got a really nice VS Code-based environment, which we're going to keep building on to make it into a really, at the moment, it'll launch your Cmajor code and run it, but eventually we'll have like embedded windows in VS Code to do instrumentation and things on what you're running. Coming soon, we're going to start our work on our playground for pretty soon and visual editor. And that's it, really. Can you have a go? Yes, because it's out now. Docs and the main site is all over at cmajor.dev. We got our GitHub is, I think, gone public, so go give us a star and have a look through the code. We also, Stefan asked us to mention that there's already Faust support out there. You can already, in Faust, you can already emit a Cmajor version of your Faust program. And that's it, yeah. Any questions?
Thank you. So we've got about 8 minutes, I think, for questions. So one here.
I was slightly confused with the JUCE export thing. Was that plugin running the JIT, or was that?
No, that was a native one. Okay. There are two different ways you can run Cmajor in a plugin. One is with our JIT plugin, which will load any old thing and JIT it. And the other one is to export, use the export tool. So you say, hey, export this patch as C++, please, and it'll just create a folder full of JUCE junk and code and blah, and then you just build that, and that's the plugin you were seeing there. So that'll be slower because that's not using the JIT. But it is, if you do want to actually ship a native plugin as a VST or AU or AAX, then that's the safest way to do it.
Does it also generate all the UI?
Yeah, it embeds the HTML and the JavaScript that you need for the UI. So that was all running as, like the plugin itself embeds a web browser in its UI, loads, and then serves its own resources secretly behind the scenes. So this is the idea. Eventually, we'll be able to go onto our website, entirely in a browser, get your whole UI going, write all your code, test it in the website, download it as a VST, which is just a VST, and it'll actually have the web stuff running in your DAW.
Thanks for an excellent presentation. 2 questions. If the JIT makes it work faster, then I guess you would need to embed some kind of, like your actual algorithms in the Cmajor language. How do you protect those? And the second question is, how is it licensed?
First question, if you're embedding your Cmajor code, we actually have a binary version. Our command line tools, you can say, take the Cmajor and give me a binary blob, basically a binary AST. So it's not assembly language, it's very optimized, and it's also very quick to load. So you can embed that, and I mean, it's reverse engineerable, but so is assembly language, you know. It's pretty harder than assembly language to reverse engineer. What was the second question? Well, the license. We want everyone to use it. All the code that's up there is currently ISC licensed, so permissive. You can embed the JIT engine, which is closed source, but it's under a EULA that lets you use it for commercial use or whatever you want. So it's frictionless is the idea for now.
So there's a C++ API. Are there also bindings for other languages, or is that internally using a C API that's now being exposed through C++? Or?
We haven't done any other language bindings yet. It's a COM API. So you could, anything you can wrap a COM object up into, you could do.
COM.
We have a JavaScript bindings, I say. But okay, COM, I mean, we all hate COM, but sometimes you just
no judgment from me, but yeah.
No, I'm not a fan, but sometimes it's the only game in town.
All right, 2 questions.
Oh, we're both going one at a time, please.
I've got 2 questions. Are you able to code an object-oriented fashion and Cmajor? And does it come with DSP modules around and filters?
Can you code in an object-oriented style? It's a little bit object-oriented. We don't have virtual polymorphic classes, but you can write a struct that has member functions. So it uses the sort of stuff that you can use in real-time code tends not to be polymorphic objects anyway. So but this is V1 of the language. If people really want polymorphic inheritance, then maybe we'll think about it. I don't think they will somehow. What was the other question? I've forgotten already. My brain's. DSP, does it come with more DSP modules? Well, the ones that Harriet went through there is a quick list of what we've done so far, the basics really, and we're going to be continuously expanding on that. Hopefully other people will start creating them too. And because all these DSP, they're not special cases. Anyone could write the same thing. They're not baked in or anything. So you can. Hopefully that will keep growing.
At this point, would you recommend pointing people who want to get into audio development towards Cmajor already, instead of confronting them with C++ and JUCE?
Well, yeah, I would. I mean, I'm a bit biased. I think it's a much shallower learning curve. So I think as well, like this VS Code extension, like I don't know, we only did this a couple of weeks ago, and it's like the fact you can just go install and then you're running DSP code with like 1 click. I mean, that's even easier than running it's certainly easier than trying to run C++ in VS Code. So I mean, yeah, I would recommend that, but then that's why I'm here doing that.
Hi there. Oh, that's loud. I was curious about the type system for the graph.
Yeah.
So, well, first of all, sort of what types are available in the graph? Obviously, you're going to have things like floats, FFT buffers, but then also thinking about value, ranges, dBs, voltages, and then back propagation of things like the enumerated types that you were declaring. And I just wondered what sort of type safety is built into the language so you can't accidentally blow something up that way.
It should all be type safe. I mean, you can use any types you want. The primitives, we obviously have the basic primitives, your floats and your doubles and your bools and your ints. But we also support structs. So, for example, MIDI going in would go in as a struct, and it's a strongly typed language. So, and the mechanism that actually gets the events in and out of a running processor will check the types. So you shouldn't be able to blow it up. And there are no pointers, so you can't pass a dodgy pointer or I don't think there is any way you could blow it up by the numbers going in. You could send an out-of-range float, I suppose.
Yeah, I suppose I was thinking about the sort of semantic differences in different types of floats. You can represent all sorts of things in a normalized float. some of which might be a voltage, some of which might be a frequency.
You could wrap them in a struct. I mean, you could wrap a float in a struct, and it will be treated as a 32-bit thing, and it'll be very efficient. But the type system will then stop you doing the wrong thing. So yeah, you can certainly do that, and we already do that for a few types.
Oh, okay. Hey. My question is there any way of loading like an external binary into Cmajor? I'm not necessarily talking about a WAV file, but let's assume that I have some complex neural network that I've built, and I want to sort of call the inference path of the neural network, which is stored as an ONNX or as a TF Lite.
Yeah,
Would that
you can.
be possible?
Yeah, you can. We have like in the manifest, the JSON file that you saw for a patch there that you saw on the screen when Lucas was doing the demo. That's where you would declare anything that imports. I mean, we obviously read audio files, but you can embed any kind of structured JSON data in there. So you could just generate JSON with all the numbers you want in it, and that will go in and get baked down at compile time into a packed floats or whatever you need for your actual in-memory data type. And we can extend that. We can add new different file types that our runtime could read. I mean, actually, that's not a bad request with just a raw binary file. If you just wanted to dump a huge binary file in there, we could have a file format for that. So, but yeah, essentially any object we can represent, you can get the data in there for it.
I think that's all we've got time for. So thanks for a really interesting talk, really exciting project.
Thanks very much.